In this problem, we're thinking about a multiple object problem where the two objects are not touching and moving together, but they're moving together due to the fact that they're connected with a rope or string. In this question, we have two masses connected by a string. It goes over an ideal massless, frictionless pulley. The boxes are not moving. And the question is, what is the minimum coefficient of static friction that would maintain this situation? You're asked to give your answer in terms of the two masses, M1 and M2. Okay, so this is a classic question with multiple objects but connected by a string. And it's clearly a dynamics question because it has to do with forces in motion. So we're going to use our typical analysis for a dynamics problem. We're going to draw free body diagrams, and because these two objects aren't pushing and moving together and touching, we can't lump them together, right? Because they might be feeling forces in different directions in each other. So our first step is going to be to draw free body diagrams of each individual object, and then do some analysis and planning from there and see if we can figure out what our goal is and a plan to get there. So why don't you see how much of that analysis and planning you can do? All right, so here's my two free body diagrams. This is mass one. This one has a normal force because it's sitting on the surface. And of course it has the weight force. It has the tension pulling it this way, and it has the friction resisting the slide. It would slide this way, so the friction force is that way. And I've made this the maximum static frictional force because if we're using our minimum coefficient of friction, that means it's about to slide. That's the minimum coefficient that would be just keeping it from sliding. So that's why I've put this at the max. Then my second mass is a little more simple because it's not touching the surface. The only thing pulling on it besides gravity is the tension. It has the tension force up and mg down. And notice it's m1 on this one and m2 on this one because it's two different masses. Oh, it's always good to put my xy coordinate system in. Let's put that in there. Standard xy coordinate system in this case. Okay, now I've also put in the things that make these multi-object questions special and that help with the problem solving. Right? Both of these have the same magnitude of acceleration. I drew it as if they were moving in case you later encounter one where they're moving, you would know what to do, right? This one would be moving this way, this one would be moving this way, different directions of acceleration, but they would have the same magnitude. In this case, the magnitude is 0. So really, I probably shouldn't have drawn these arrows. I should have just written A equals 0 on both of them. I just wanted to show you what you would do if this was a question where they are moving. All right, the other thing that this isn't different because you've done tension before, but because they're connected by this massless rope, they both have the same tension force. So the T here is the same as the T here, and whatever the A is the same as the A here, even though they might point in different directions. So A equals 0, tension and tension. That's what unites these as a multi-object problem. All right, now our goal is the coefficient of static friction, the minimum one. And my plan is the Newton's second law, sum of the forces in X equals MAX, sum of the forces in Y equals MAY. And I'll do it for this one. And then I'll have up to 4 equations, right? X and Y for each of them. I'll look at those 4 equations. I will also use our equation for friction, and hopefully I'll be able to manipulate them to solve for this mu s. So that's my plan. I'm going to execute the plan now. Why don't you pause and see how much of the execution you can do? All right, here goes my execution. I started over here with the sum of forces in X equals MAX for this one. The sum of the forces is minus the frictional force plus the tension force. Both of those are completely in the X direction, so I don't need components. It equals 0. Then I plugged in my equation for friction right here, this one. And then I realized, aha, here's how I get my mu s, my goal in, so I started solving for it. So here, the mu s times the normal force equals tension. I subtracted this over to this side, then I cancel the minus sign. Then I solve it for mu s, and I get mu s equals the tension over the normal force. Okay, I don't know either of these yet, but hopefully my other equations will help me get these so that I can get this side in terms of m1 and m2, which is my goal. Okay, then next I do sum of the forces in Y. Sum of the forces in Y equals MAY. That's the normal force minus the weight force. Oh, and again, I forgot to mention all of these equal 0 because the acceleration is 0 in both directions. I solved that, and I got the normal force equals m1g. So already I'm ready to plug in here, but I'm going to wait till the end. You can see all the ones I've underlined in red are the ones I'm going to use. Then I got the sum of, then I went to my second free body diagram, and notice in my multi-object problem, I do have to use usually the Newton's second law, sum of the forces in X or Y, or maybe both, equals MAY for both this object, and put them together. So here, I have the sum of the forces in Y equals mass times acceleration in Y, but now for this object. That's the tension minus now m2g, the weight of the second object, and again equals 0 because it's not moving. If it was moving, this would be the acceleration here, and in the x direction, I'd have that same acceleration here. But since it's not moving, it's just 0. I can solve this now for the tension force, which I can plug back in here. Tension equals m2 times g, and then I can combine it all together with this original equation. So I've combined this, this, and this, all the ones underlined in red, and plugged in the tension force from here, the normal force from here. Gravity cancels, which is handy because I kind of didn't want that in my final answer. And this is what I'm getting. Okay, so now I want to do some monitoring. I look at my thing, and this is saying the bigger the second mass, the bigger M2 is compared to M1, the bigger a frictional force I'll need, which is totally true. Like the more downward pulling on M2 compared to the M1, the bigger the friction force is going to be, right? And if this one was really huge and this one was really light, I would expect I wouldn't need such a big frictional force, and that would be this one big, this one small. That would be a small number. I also want to check my units. Mu(s) is unitless, and this is a mass over a mass, which is unitless. So I feel like I'm looking good for my answer, and I'm going to put it in a box.